so ready? Yep. Alright, so you're on your notes from like a week ago. Okay, and we skipped the page right here that says calculator use required. So we're going to do that one because we skipped it and we got to go back and do it. So, it should look like this. Does anybody need it? And I'll get it for you. Anybody absent this day? No? Okay, so it says an object moves along the x-axis with initial position of x of 0 is 2. The velocity is given by v of t equals 3 sine t. Okay, first thing, when does the particle change directions? Now, what would be really nice is if we had a graph of velocity. But wait, you have a calculator. So, graph this function on 0 to 4.5. Okay, if you graph it on like a standard 10 by 10, you're going to be looking at a bunch of stuff that you don't need. Okay? So, 3 sine t. Ooh, look, it's already in there. Window, nice, great. You might be in degree mode. Oh, take your one off. Oh, is this the first day you've used a calculator?
No, I can't see the freaking flash thing.
Okay, got it?
No. Look at this.
Okay, so what could be wrong? Ready? This is fun. What's wrong with it? Look at my y-axis and look at yours. You're zoomed out. Also, if you hit window, you're going negative 40 to 40. So that's too big. So let's go negative 10 to 10. Okay, voila. Perfect. Okay, so sketch your graph on your paper. How do we know? Remember, this is a graph of velocity. How do we know when our particle changes directions? What would need to happen? It needs to pass through the x-axis, so boom, find it. You can do it. Okay, what are we doing under second trace? Okay, 0, option 2. And then remember, you can use the cursors or you can just pick whole numbers on either side. So for example, this is 1, 2, so I'm going to put 2 and 4. So watch, if you want to do the shortcut way, my left bound is 2, my right bound is 4. And then you don't have to piddle with the little arrows. You still get to skip guess, and it'll just give it to you. So that value is t equals 3.1415. What number is that? That's pi, right? And think about, does it make sense that sine would hit at pi? What's the sign of pi? 0, right? Okay, so justify, because why? V of t did what? Changes what?
Positive.
Changes sign. And I'm not even going to say like which way it changes sign, because it's not asking if it's a min or a max. It's just asking when did it change direction. But if you did put that detail, it wouldn't be wrong. Okay, next part. When is the particle traveling to the left? Where do I want it to be, above or below? Okay, so it would be from 0 to infinity? Just the end of the graph, which is 4.5. So I would put from 3.1415 to 4.5. Because if it's below, what would I say about v of t? Less than 0, good. Alright? Part C says, find the acceleration at 4. Now, could you take the derivative of that function by hand? It would be possible. Yes. Okay, but you have a calculator. Do you want to do it by hand or with the calculator? Yes. Okay, right answer. So, we want to find the slope of the graph at 4. So, second trace. Which one is the slope?
6.
Okay, option 6. dy dx stands for derivative. And then remember, you tell it where you want the derivative. You want the derivative at 4. Now, think about why it came out negative. What's your slope at that point? Is it going downhill? Yeah, so that makes sense. So, on your paper, you would write acceleration at 4 is v prime at 4 which is negative 1.9609. Okay, part D. Is the velocity increasing or decreasing? Okay, think about, if acceleration is negative, what is the velocity doing? Huh? It's going down, right? Because it has a negative slope. So you would say it's decreasing because v prime of 4 less than 0. So remember, for velocity to be increasing or decreasing, you would just care about the sign on acceleration. Okay, but then part E says, what about the speed? What two things do we have to consider for speed? The acceleration and the velocity. Now, how are we going to find the y value at 4? Let's say we needed the exact value. We know it's negative because it's below, but how could we find it? Okay, you could do it in the table. That's probably the easiest way. But pretend like it was like a complicated number not in your table. Hit second quit. Do alpha trace, so green trace. Pick y1, and then parentheses 4. And remember, that will also tell you the y value at 4. Now, if it's a whole number, it's going to pop up in your table and you could scroll. Okay, but that would be the way to find your y value at that point. So, my v of 4 is negative 2.2704. My a of 4 I just found was negative 1.9609. Remember, we know that from way up there. So, is my speed increasing or decreasing? Increasing because why? They're both negative. They have the same sign. So, speed is increasing. Okay, now I'm going to write something wrong. Think in your head, but don't say it out loud. Also, don't write what I'm writing or else it'll be wrong. Okay, speed is increasing because v of t and a of t have the same sign. What's wrong with it? Yes, this is like for an interval. Like if you were giving a chunk of time, you would make it general. But if you're being specific, you want it to be at 4, then you have two ways that you could do it. You could say at t equals 4 somewhere, or you could just make these 4s. Okay, which is much better. Okay, part F asks you to write the equation for position. Okay, so if we have velocity, how would we get to position? Yes, antiderivative. Good. So, v of t is 3 sine t. This is what we were doing last week. Okay, I'm going to integrate on both sides. What is the integral of velocity called? Position. And then think about your snow cone, snow cone. Okay, remember antiderivatives, you always go up. Good. Negative 3 cosine t. Are we done?
Plus.
Yes, plus c. Now, remember, you cannot leave that c open. They always are going to give you some sort of information to find it. So go back up and look. What did they tell us about position? X of 0 is 2. Very good. And so what that means is that 2 is the answer when we plug in 0 here. So we have 2 equals 3 cosine 0. And then cosine 0 crosses out? Or does it? Yeah, that's a 1. So negative 3 times 1 is just 2 equals negative 3 plus c. Which means that c is what? 5. So x of t is negative 3 cosine t plus 5. Okay? Then in part G it says, okay, well now we have position. What is the position at 4? Well, then what would we do? Yeah, plug in 4. And you have a calculator, so you should be able to do that, right? So negative 3 cosine of 4 plus 5. Should come out to 6.9609. What would I write on my paper? How would I label what I just did? X of 4. Good. And then 6.9609. Okay, now, quick question. If my position at 4 is a positive 6, which side of the origin are we on, the right or the left? Okay, so on my number line, here's the origin. I'm over here at 6. X of 4 is 6.9609. What is my velocity that I found earlier? Right here.
2.27.
Negative, what direction does that indicate? To the left. So if I'm here and I'm going that way, am I going towards or away? Towards. And then you would say, so X of 4 means that you're on the right, but V of 4, and I'm not even going to give the number, I'm just going to put less than 0, okay, means that I am traveling left. Make sense? So then you would say, answer is therefore towards. Okay? So your calculator can help with a lot of that stuff. And I think there are a couple of questions on homework too where you need a calculator to answer them. So, what I would love for you to do now is in your normal notes, we're going to take like 1 page of notes and then we're going to do the notes that you picked up because it's a bunch of tables and stuff. Okay? Yeah, just like what you normally take notes in. Okay. Alright, you can title your notes Riemann sums. Some people say it Riemann sums. I don't know which one's right, nor do I particularly care. What did you say? I do love math, but it's like a debate. I know, but it's like if half the people say one thing, just so you know, it's ever called a Riemann sum, that's the same thing. But I always heard it Riemann. So, the world will never know. He died long ago, sadly. Okay, so an integral from a to b of f of x dx is the exact area between the function and the x-axis on a to b. We already learned that, right? So when you have an integral from a number to a number, that measures the amount of space between the curve and the x-axis on that interval. Okay, so the problem is all the equations that we looked at yesterday were linear or they made perfect circles. Obviously, that is not the real world. That's not how everything works. So a Riemann sum, I'm going to abbreviate that to not have to write it again. Okay, but you can just put a little arrow to help yourself remember. A Riemann sum is a method of estimating non-geometric areas. So if it's not a perfect triangle or a perfect rectangle or a perfect half circle, okay, then you could use a Riemann sum to estimate that. Okay, so if you pay attention on these first couple of examples, we probably won't even have to do all of them, which is the goal, right? So, pay really close attention on these first two. So let's say that you have a function, I don't know, that looks like that. There's our f of x. Okay, and then let's say a is here, b is here. Okay, the integral from a to b, then, would be represented by the area right here from, I'll do it in yellow, from a to b. Okay, so that's my exact integral, is that area. Now, the problem is there's no way to break that up into perfect little shapes. So what a Riemann sum is you're going to chop the area up and you're going to make rectangles about the same height to estimate. So the first thing that you're going to do is you're going to divide A to B into n subintervals. You're going to divide A to B into n subintervals. Now, for the first one, we're just going to use 4 because it's easy. So I want you to take your A to B, I want you to cut it in half, and then I want you to take each of those halves and then cut it one more time in the middle on both. So I'm going to cut it here and I'm going to cut it here. So now I have 4 sections of my area. So I broke it up like this. Step number 2. You are going to create n rectangles using the same L, R, or M y values on each interval. L, R, and M stand for left, right, and middle. You will probably not forget that, but you can label it if you want to. This example that we just did is going to be a left. So what we're going to do is we are going to take each interval, we're going to use the left y value, and we're going to create a rectangle of that height. So watch. For A to B, these are my 2 y values, right? Here and here. I'm going to pick the one on the left, and I'm going to draw a rectangle. Now you do that. So ready? Go to your left end point, cut it across, make a rectangle. Now we're going to go to the second interval. So these are my y values. I'm picking the left one, and I'm going to make another rectangle. My third little chunk of the graph, I'm going to use this left end point, and I'm going to make a third rectangle. Doesn't? Oh, but it looks cool up here, huh? Okay. Do you want a marker? No. Did you say that would make you a dork? Oh. I was like, okay, backhanded compliment. I want to be a dork like you. Okay, now look. You have now created 4 rectangles. Now think about, remember this is an estimation. If I add up all of those areas, is it going to be pretty close to the real area? Yes, that's what a Riemann sum is. Okay? So we created our rectangles. Step number 3, you would find areas of each rectangle. And then the fourth one, your integral from A to B, f of x, would be approximated by, we're using like a squiggly equal sign, a1 plus a2 plus a3 plus dot dot dot. Now in this case we only have 4 rectangles, okay, but you could have, you know, God forbid, like hundreds of rectangles, but they'd never make you do that. Okay? The next example we're going to only draw, because the steps are the same, is going to be a right Riemann sum. Okay? So try to draw the same picture-ish. Okay, make your graph go kind of up. We're going to use still 4 subintervals. So here's A, here's B. Cut it in half. Okay, and then I'm going to cut each of those sections. I'm going to cut it in half, and then in half again. And then I'm going to draw in my little divider lines to splice off my 4 sections. So I have here, 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 here. Now, this one is going to be a right Riemann sum. So when I'm choosing the height of my rectangle, let's say I'm doing it for this first one. Which endpoint am I going to use if it's the right? This one, right? And then I'm going to cut across and down. So do that on your paper. So take the right endpoint, across, down, and you're going to make a rectangle.
So the first one was the left.
The first one, yeah, and I had labeled it left kind of sneakily, but yeah, the first one's left, this one's right. So we're now going to take our right endpoint, cut across and down. Then cut across and down, across, down, across, down.
How do you know which one to use?
It will tell you on the AP test which one they want you to use. Now, when you do your rectangles, okay, I want you to think about your two pictures. On this one that we just did, how does the area of your rectangle compare to the actual area? Is it too big or too small? For this one. Your orange rectangles are too much. They're an overestimate, okay? So I'm going to write right here, this is an overestimate for the increasing function. Okay, because your area is too much. Each of these little sections here, okay, those are all extra. And so technically that's like an error, right? It's too much. Okay, then go look at the first picture we drew. Is that one too much or too little for the blue rectangles? That's a little bit too little. So this would be an underestimate. Okay? And now we're going to go to that sheet you picked up. Ready? All right. First thing that I'd like for you to do is we're going to sketch this graph, but like super sketched. So don't try to like make a really specific graph. That's a waste of time. So 0, 1, 2, 3, 4, 5, 6. And then overall, look at the y values in the table. Are they getting bigger or smaller? Yeah, all my points, eventually they're getting higher each time. So I'm just going to do here, 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 here. Don't try to like be too specific. It doesn't really matter. You just need points on your paper. So this one is 5, 7, 8, 10, 13, 16, 20. Now, if I were to connect each of those dots, okay, and make a function, okay, then my integral would be the exact amount of space underneath that curve. Right? Okay, so there's my exact integral. Now let's talk for a second, since we talked about this yesterday. In order for you to know what you're measuring, you multiply the x and the y units. So let's read our little question. Okay, it says, coal gas is produced at a gas works. Pollutants in the gas are removed by scrubbers, which become less and less efficient as time goes on. The following measurements made at the start of the month show the rate the pollutants are escaping in the gas. Graph the data in the table below. Okay, so think about it. You have gas, right? Okay, there's pollution in it. What's the scrubber's job? They're supposed to what? Supposed to remove them, but what happens over time? They become less efficient. So at the beginning, are they letting a lot of pollution out? No, they're doing a good job. And then as time goes on throughout the month, as the scrubbers get old, they start letting more and more pollution out in the gas that they're producing, okay? So this is measured in tons of gas per month. And your units are in your table, so we're not making that up. It says it right there. And then down here, we're measuring months. If you did length times width, you would have tons per month times months. What would your units be? Tons. Tons of what? Tons of pollution. Very good. So the integral from a to b of this function f of x represents the number of tons of pollution over, and then we'll say 0 to 6, and that's measured in months. So remember, to know what you're measuring, you just multiply your X and your Y together. So if it's tons per month times months, that's tons of pollution. So that would be how much pollution was leaked into the gas. Okay, so now let's do our new stuff. So our first sum, we're going to use a left Riemann sum. So break it up. No, we're not breaking those up. Each of those is going to be a rectangle. Now, question, as I draw my rectangles, which endpoint am I using first? Left. Now, on the AP test, they're just going to pick one, left or right. They won't make you do both. I'm going to make you do both to practice. Okay, so left, which one am I going to pick?
The 5.
5. Draw it across, shade in your rectangle. 7 and 8, which one am I going to pick?
7.
7. Draw it across, shade in your rectangle. You get what you're doing? Okay, so you should be drawing here, 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 here. Now, let's say that I want to find the area of each of those rectangles one at a time. So look at my first rectangle right here. Okay, area, I put an A1 there. How wide is it from 0 to 1? How tall is it? 5. So 1 times 5 plus. That's my first rectangle. 1 times 5 plus. Okay, second rectangle. From 1 to 2, how wide is it? 1. How tall is it? 7. Plus. Now, do we have to write the 1 each time? Okay, no, but we're going to for this first example. From here to here, how wide is it? Then 8. Okay, you get the pattern here? So my next one is 1 times 8. What's my next rectangle? So I did this one, this one, this one. What's my fourth one? 1 times 10. Next one. 1 times 13. Next one. 1 times 16. Now, question. Will I ever use 20? Does 20 have a rectangle over here? No, then that one gets skipped. So when you're doing a left Riemann sum, you're going to use all the y values in the table, but you're going to skip the last one. Because he never gets to be the first side on a rectangle. Because he's the end. Okay? And then you would add that up, but you're not doing that because that's a waste of time. Okay, part B. So this is my left. Done. Okay, part B. We're going to do a right Riemann sum. So ready? Here's your right one. I'm going to do it down here. Okay, let's fix our picture. So this time we're going to do all the right endpoints. So for my first one, between 5 and 7, which height am I going to use? 7. Then I'm going to use 8. Then 10. Here. Here. And then here. But remember, we're still just adding up areas. Now, is it okay if we don't write the 1 this time? Is everybody good with that? Okay, because if that's your width, it's not going to change anything. So ready, first rectangle. Which height are we using, 5 or 7? 7 plus, next one. 8, next one. 13, 16, 20. Who never got used in the table? The first number, the 5. So it would be 7 plus 8 plus 10. 8, 10, 13, 16, 20. And then you're done. Now, quick question for each one. For my left Riemann sum, was it over or under? Left was the first one that we colored. Under. What about the one that we just drew, the red one, on my picture? That was an over. Okay, because I'm going to put your rectangles were bigger than the actual area. Make sense? sketch your picture down here just with your dots. 1, 2, 3, 4, 5, 6, and then just make your dots going up again. So we did a left, we did a right. Now we're going to learn the only other type, which is a midpoint. Here's how a midpoint works. Okay, I'm going to sketch my little picture here again. For a midpoint, you are going to cut your graph into bigger rectangles because you're going to leave one in the middle. So when I split this up, I'm going to split it up. Skip one, split it up. Skip one, split it up. Skip one, draw your last divider. And then what point do you think I'm going to use if it's called the midpoint to set the height of the rectangle? The one in the middle. That's right. So I'm going to use this height right here. And then I'm going to shade it in. And then on my next rectangle, I'm going to use this height right here. And then I'm going to shade it in. And then that height. And then shade it in. Now let's label only the points that we care about. For this very first rectangle, look at your table. Okay, this is from 0 to 2. What's in the middle? 1, right? So what is 1's y value? So that first one is a 7. What about from 2 to 4? What's in the middle? 10. And then from 4 to 6, what's in the middle? 16. So these heights are 7, 10, and 16. Now question, is my width of each rectangle still 1? No. How wide are they now? 2. So your area here would be 2 times 7 plus 2 times 10 plus 2 times 16. Now, quick question, if all of those widths are 2, does it make sense to keep writing 2 over and over again if we could just pull it out to the front? Okay, probably not. So I would do it, or little star, you can do that. Now, the caveat to that is that you can only do that if it's the same width every time, and we'll look at some examples where that's not true. Okay? Now, question, is your estimate over or under or not sure? Okay, think about it. Like on this first triangle right here, or this third one, that's not enough, but that's too much. What's going to happen with that error? It's going to kind of cancel out. Now, is it going to cancel out perfectly? No. Okay, but then look at the next triangle. It's like, oh, this is too little, but that's too much. So they kind of cancel out. And then same thing here. Not enough, but too much. So this is more accurate. More accurate than a left or a right. And the reason why is because instead of all of your error being too much or all your error being negative, you have a little over, a little under, and they kind of cancel each other out to an extent. Okay? So that is more accurate. Alright. You ready to do another one? Do we have to draw the picture? Well, maybe we won't draw the picture. Okay. Next one that we're going to do, yeah, let's do number 2. Okay, I'm going to show you how to do it without drawing the picture. If it's too soon and you need me to go back and draw the picture, I totally will. Okay, so look at your first one. We want to do a left Riemann sum. So from 0 to 2, how wide is that interval? Think about how wide that rectangle would be. How wide? 2. Which would be the left y value? The 88 or the 45? On the left would be 88. Plus, what's my next interval from 2 till 5? How wide is that? 3. Which y value is on the left? The 45 or the 16? 45, because remember, the left is the one that's going to come first. Then from 5 to 7, how wide is that? 2, but what is my left y value? 16. Does that make sense without the picture? Okay, now for your right, what's going to be different? Instead of skipping the last one, you're going to skip the first one. Because for my first interval, from 0 to 2, it's still too wide, but my right Riemann sum is going to pick the 45. And then from 2 to 5, how wide is it? 3. But what is my right endpoint? 16. And then for my next one, from 5 to 7, the width is 2, but you would be choosing 0 there. Okay? Okay, now, for actually doing the over and under, it's a little easier to visualize it. I'm going to do a really quick sketch. You can do it or not, I don't care. But it's not always that a left is under and a right is over. It depends on which way the function's going. Which way is this going, up or downhill? Okay, so look, if it's going downhill and I pick like a little section, where is the left estimation going to be? Too big. What about a right estimation if I do, say, this one here? That would be under. So a left is going to be an over estimation because your rectangles would all be cutting too high. Versus a right, like this one, okay, would always be too small. It would be an under estimate. So you can't just memorize it. You just have to think about which way the function's going and whether the left or the right would be too big or too small. Okay? Number 3, all the decimals are annoying, so we're going to skip it. Not that it's too hard, but we would have to write a gazillion numbers. So we're going to skip it and do... Let's do number 5 with the little chart. That way we don't have to make our own. Okay, so we have the rate of fuel consumption in gallons per minute. I'm going to label that here. Gallons per minute. Recorded during the plane flight is shown in time is measured in minutes. Okay, first question. Look at, and this is an actual AP question. Interpret the meaning. If I multiply gallons per minute by minutes, what's left over? Gallons. Gallons that were what? Consumed. Very good. So the integral from, what is it asking us to take right here? 0 till 90 of R of t represents the number of gallons consumed. Now, when were they consumed? From 0 to 90 what? Minutes. Very good. Okay? And technically it might be better to say the number of gallons the plane consumed. Okay, but you get the idea. So you multiply gallons per minute by minutes, you get gallons. What were the gallons doing? They were being used by the plane. Okay, now now read through this. What are we going to actually use? What type of Riemann sum? A left. Look right here. A left Riemann sum. How many subintervals, how many rectangles are we going to have? 5. So they're going to have to tell you those two details. So I'm going to go from 0 to 30, 30 to 40, 40 to 50, 70, and then 70 to 90. Those are my 5 subintervals. Now, is the width the same each time, or does it change? It changes, so we're going to have to go one at a time. Ready? First rectangle, from 0 to 30, how wide is that? 30. And what is my left endpoint? Is it the 20 or the 30 if I want the left one? 20. Very good. Okay, plus. Next one, I'm going from 30 to 40. How wide is that? 10. Which of those is the left y value? The 30 or the 40? The 30. Plus. My next rectangle is from 40 to 50. How wide is that? 10. Which is the left y value? 40. Okay, next one. We're on the 4th rectangle. From 50 to 70, how wide is that? 20. And which is the left y value? Would I choose 55 or 65? 55. And then for 70 to 90, how wide is it? 20. And which endpoint? 65. Okay, then next question. So it says interpret the meaning. use a Riemann sum. Is your approximation above or below the actual value? Okay, well think about it. If I use lefts, let me just cut up this little piece right here. I use the left side. Is that too big or too small? Too small, so it's an underestimation. Okay? Alright, turn the page, let's do one more off the back. Let's do this first one right here. This one's another midpoint. So it says, suppose you're a navigator aboard a cruise ship going to Gilligan's Island. Okay, the speed of the ship is measured and recorded in the table. Estimate the distance it's gone from 7:30 to 9:30. Using 30-minute subintervals and using a midpoint sum. So the integral of v of t dt is going to represent, multiply your units together. If I do miles per hour times hours, what's that going to give me? Miles. And how are we getting the miles? Who's doing them? The cruise ship, right? So it represents the number of miles traveled from 7:30 to 9:30. You could put PM on there if you want. Okay? So it represents the number of miles the boat traveled from 7:30 to 9:30. Now, we want a midpoint Riemann sum. Remember, midpoint means that you have to skip one each time. Now, they also gave you another hint. They said every 30 minutes. So if they're checking at 15 minutes, that's the one we're skipping. Okay? So ready? From 7:30 to 8, what is my midpoint y value? 25. I'm going to circle it. Okay, then from 8 to 8:30, what's my midpoint y value? 22. From 8:30 to 9, what's my midpoint y value? 10. And then from 9 to 9:30, 26. So when I set up my thing, now how wide is each subinterval? What's my delta x? Or in this case, I'll put delta t for time. 30 minutes. Now, if this is measured in hours, we have to be consistent. So rather than putting 30 minutes, how much of an hour is that? A half. So my t is going to be half an hour. And now remember, that delta x is the width of each rectangle. So you would do 1/2, and then you would add each of the midpoints. So it'd be 25 plus 22 plus 10 plus 26. Now, you could do half of 25 plus, half of 22 plus, half of 10, but that would be annoying, and this is the same, so it's better. Okay? Alright, let's do one off your homework. Why don't y'all just do the first one? First one on there. So I want you to underline what type of sum you're using, so left or right, and then how many subintervals you should have. So for part A, which side are we going to use? Right? And then we want to go for all 10 minutes. So and then second question, is it the same delta x every time where we can like pull it out to the front? Sadly, no. So from 0 to 1.5, how wide is that? 1.5. Which y value am I going to use? 120 or 180? 180. Plus. From 1.5 to 2, how wide is that? 0.5. And which is my right endpoint? 241. Plus. Next one, from 2 to 4, how wide? 2 units. What's my right endpoint? 360. Plus. 4 to 6.5, how far is that? And then my right endpoint would be 480. Y'all get the idea? Okay, can you start the midpoint one now? A midpoint, what do we have to remember to do? You have to skip 1. And is that going to change your delta x? Yeah, because you have to skip 1 in the middle each time. So like for my first one, I'm going to go from 0 to 2, and what's my midpoint value going to be? 180. So it would be 2 times 180. Next one, I'm going to go from 2, skip 4, go to 6.5. How wide is that? 2.5? Oh wait, 4.5, sorry. And then what's my middle y value? What's my middle y value between 2 and 6.5? 360. Okay, plus from 6.5 to 9, how far is that? 2.5. What's my middle y value? 500. And then for your last one, from 9 to 10, how wide is that? 1 unit, and the midpoint is 605. Okay? Now, do not add those up. Okay, waste of time. You don't have to do it on the AP test. You don't have to do it here. Okay, go ahead and just skip number 3, and we'll do that one at the beginning of class tomorrow if y'all remind me. Okay, skip number 3. What's wrong with number 3? Does it have a table? No, but we'll do that one tomorrow. Okay? Great job. Only homeworks 2 and 3 are due Friday. So don't stress about this one. It should be easy, but you don't have to turn it in Friday. Bye, Nora. Have a good day. Bye. Have a good day. What's wrong with you? You need a carrot. Come here.
I already ate. I'm good.
Really, I just want You're kind of sleepy today, huh?
Very, actually.
Why is that?
Because I got, like, good sleep last night. Like, today I slept until, like, 8:30. And usually I wake up at 6:30. So, like,
Wait, you slept longer, so you're more tired?
yeah, when
Yeah,
I sleep
that's the
more,
thing.
I get more tired.
It is?
It's a huge thing, yeah.
Like, when I run on 4 hours of sleep, I'll be like...
That's why I'm never tired, is because I never get enough sleep. It's genius.
Okay, but after a while, it, like, gets to you. I mean, it feels nice, like, maybe once, like, sleep for, like, more than 8 hours. After that, it just...
Yeah.
No, like, even if I do, like, if I sleep more than, like, 7 hours, like, I'll be so tired the next day. Like, I'll be like... Cause my body's just not used to it.
Yeah. That makes sense. Is that like a real science thing, though?
I made it up for my body, so now it is. No, I mean, it's an actual thing. Like, if you're not used to sleeping a lot, when you do sleep a lot, you feel more tired.
Bye, Kevin. Have a good day. Bye, Chew.
One single day, also continue to sleep all day.
See y'all tomorrow.